Hello everyone, my name is Marcos Underwood. I'm the Chief Scientist at MSI-Direct, working with them through my consulting company, Tutuli Enterprises. Today I'm going to be speaking to you about a new method I've developed that determines an optimized reference spectral density matrix for MIMO testing. This new method generates a positive definite reference spectral density matrix that approximates a pre-specified reference spectral density matrix with the least drive power and approximation error. It modifies the off-diagonal elements of a pre-specified SDM, but keeps its diagonal elements fixed. It takes into account limitations that may exist in testing systems and/or a facility as a constraint. It's unlike other methods that are out there like this. Typically, a more uniform and diffuse acoustic field results from MIMO DFAT tests. It reduces control errors for MIMO random testing with more linear responses for both types of tests. It's synthesized by the Jaguar's underlying adaptive optimal MIMO control optimization capability. I'm going to be showing you results from a previous MIMO DFAT test. It was run with narrowband digital MIMO control, 20 hertz to 10 kilohertz, like the rest of the tests I'll be discussing. But this test used 15 drives, 15 control mics, and 15 speaker stacks. More drives and controls were possible, but this was a typical configuration, so we decided to focus on it. Additional monitor and array microphones were used to verify the achieved acoustic field uniformity. Advanced optimal adaptive control and randomized microphone placements reduce the magnitude of standing waves to reduce structural hotspots due to response enhancements, as I discuss in the paper in more detail. Limit MIMO control on test articles is possible, but was not used for the test that I'll be discussing. In this example, we have 15 controls, 21 monitor mic, PSDs overlaid on each other, as you can see. The uniformity is quite good, within plus or minus 3 plus dB for the entire frequency range. These new research testing results I'll be showing, on the other hand, use the new control reference SDM synthesis and approximate a pre-specified control reference SDM within the least mean squared error and using the least drive power. It requires also the least drive SDM power for the least approximating error during control using advanced adaptive optimal control methods. It provides a uniform and diffuse acoustic field, as well other types of acoustic fields, as I discuss in the paper. Better control of both levels, coherence, and phase are possible. The control optimization is performed at each control loop iteration using this advanced MIMO control. It results in a more linear response characteristic. Here's the result, the average of 15 controls with 4 drives and using 15 speaker stacks as before, but now using the optimal SDM reference. It's presented in both 1/3 octave SPL and narrowband PSD spectral formats. As you can see, the corresponding to the reference spectrum is quite good, within a few tenths of a dB. The individual controls for that same test, 1 through 15, are shown in this next slide. It shows that the controls, all 15 of them, are within the control tolerances of plus minus 3 dB quite comfortably. The coherence results for that same test are also consistent with what you would expect out of a diffuse acoustic field. A near approximate sync squared function shape at the low frequencies for nearby microphones, and a lower coherence approaching 0 as the frequency increases. In this case, you can see that the coherences are less than 0.4 for most of the terms in the frequency range above 1,000 hertz. Anything below 0.4 is effectively zero coherence because of the high variance that coherence shows as the coherence value reduces. This is a good example of a diffuse uniform acoustic field. Now, more recently, we've done performance using fewer speaker stacks. Here I'm showing you the average control results of using 24 controls, 4 drives, and 8 speaker stacks as compared to the 15 speaker stacks that were shown earlier. Again, the control response is close to its respective reference in both third octave and narrowband formats within a few tenths of a dB. The shape and the level is the same as before, but the lower speaker and the same control was achieved by using the optimized reference with its least power, dry power capabilities, along with advancements in the MSI speaker technology, where we continuously improve as we can the various components in the system. The individual microphones responses are shown next in third octave format, all 24 of them. And again, you can see that they are close to the reference and within the plus and minus 3 dB tolerances of the test. This new performance is due to the optimal adaptive control and optimal reference SDM, which together help to reduce the control error to the least mean squared error sense. It reduces the power needed to drive multiple speakers. And most recently, as I showed in the previous slide, achieve the same overall sound pressure level with fewer speakers. The new synthesis matches the initial reference in the LMSE sense, improves uniformity and lower coherence between control microphones as compared to previous results. It achieves better uniformity of control and monitor microphones. It produces a better approximation to a uniform diffuse acoustic field. Recent panel response studies show that the achieved field excites the structural resonances better than a response from a non-diffuse fields obtained from MISO acoustic testing, as well as other non-diffuse fields. Again, this validates the fact that the field that's being produced is diffuse, and also shows the importance, as I discuss in the paper. I discuss this topic in more detail in a paper that I'm also going to be presenting at the Shock and Vibration Symposium later this month. In any case, we achieve better rectangular control, uniformity, and coherence between control microphones over the control frequency range than we previously were able to achieve. This technology is also applicable to MIMO random testing, as you might imagine. In this example, I've constructed a 5-shaker system that can accomplish 5 rigid degrees of freedom, X, Y, Z, and 2 rotations about Z and Y respectively. It was developed to be a difficult test article. The shakers are just sitting on the floor. There's no seismic mass. There are braces to hold the test article in place and various components that loosen during the test. The stingers are used to decouple the shakers by allowing the independent degrees of freedom to move independently. The stinger bending stiffness is much lower than the axial stiffness, which is what provides the free movement of the independent axes. However, it's not ideal. It's beset with nonlinear and rattling, as well as loosening of coupling effects that make it difficult to control PSDs and coherence. And also we see low partial coherence between drives and controls at many frequencies when we don't use the newly developed optimized reference spectral density matrix. To illustrate this, we defined 2 tests identically, where one ran with the optimized reference and one did not. The tests were defined with different PSDs for each axis at 1 GRMS. There were 3 axis tests, X, Y, Z, with all 3 axes uncorrelated with each other and suppressing the 2 rotations, RZ and RY. The initial coherence was set to 0.9 between similar axes, between the 2 Y shakers and the 2 Z shakers to suppress rotations, and 0 between dissimilar axes to make the overall motion uncorrelated between the 3 axes, thereby achieving a sphere of motion according to a 3-dimensional Gaussian distribution. We determined the new optimized control reference from an initial test using pre-specified reference SDM. 2 tests were run for 15 minutes each. Test A used the pre-specified spectral density matrix, and Test B used the optimized spectral density matrix obtained with the new method. We retightened all the couplings between tests so that the 2 tests would start with the same initial conditions. In this plot, I'm showing the PSDs of the Y1, Y2, Z1, Z2 accelerometers with test A and test B shown at the same time. The 2 traces that are easiest to spot are the black trace for test A and the green trace for test B. As you can see, the trace for test B is close to the reference, while the black trace for test A diverges from the reference at various places, most prominently around 200 Hertz, where you see the black trace lower than the control tolerance. The green trace, on the other hand, and the other trace, since for test B, remain close to the reference. On the upper right-hand side, for the Z accelerometers, you see that the black trace exceeds the abort tolerance just past 100 Hertz, and also around 100 Hertz, you can see that the black trace is outside the abort tolerances from around 150 Hertz up to almost 300 Hertz. And there's other places higher in frequency where you see the same phenomena, whereas the green trace and the other traces for test B are all close to the reference. So here we're showing better PSD control with the use of the new reference. The lower 2 traces show the relative coherence between Y1 and Y2 and Z1 and Z2 for test B. The green trace is on the left is the coherence between Y1 and Y2, and the red trace is the modified coherence reference for that test. So you can see that the coherence was lowered at various frequencies due to the nonlinear and facility limitations that were present in the test. The green trace is always close to the modified reference, and on the right we see the same sort of display for the Z1 and Z2, the coherence between the 2 Z1 and Z2 accelerometers, again showing the same type of behavior. In this next plot, I show the coherence between dissimilar axes, between Y1 and Z1, between Z2 and X on the top trace, between the other accelerometers with respect to each other that were of different axes. And as you can see, the coherence is low at most frequencies, except at those frequencies where the shaker system limits how low the coherence can be made. In this case, the reference spectrum is shown in green, the modified one, and the achieved coherence is shown in black, again showing how close it is to the respective reference, and the fact that we, by and large, at most frequencies, achieved independent motion in X, Y, and Z. How do we show ordinary and partial? How do we show how linear a system is? Here's where we chose partial coherence to be the measure of linearity, because as you may know, partial coherence measures the degree to which any one drive is linearly related to any one control, with the linear effects of all drives removed. In other words, if the partial coherence is high, that control is linearly related to its respective drive. The other measure we used was MIMO coherent output power. This one's a little bit more complicated. I developed a theory for both partial coherence and MCOP in the paper, but here I'll just give you a brief overview. The MCOP is a spectral density matrix of the coherent response due to the drive vector. In other words, the coherence, the response C hat, is linearly related to the drive signals that are being used. It can be obtained in the expression I have shown there as a second equation. It's a 3-matrix product with GDD being in the center and cross-spectral density between C, control and drive, complex conjugates on either side, multiplying that inverse. It's similar to the coherent output power, which is shown as a function typically as the magnitude squared of a cross-spectral density between control and drive divided by the PSD of the drive. It's Hermitian, non-negative. It represents the spectral density matrix of the coherent response that's coherent with the drive vector, and GCC is thus the system's MIMO coherent output power. It also decomposes GCC, the control response, as shown there, as a coherent component and a non-coherent spectral density component. And this means that the coherent MCOP will always be less than or equal to the measured PSDs of the control. Now here's where I show a comparison between the PSD of Y1 and Y2 to their respective MCOPs. On the top row, I have the result for test A. And you can see, particularly around 200 hertz, that the PSD for Y1 is larger than the MCOP by a pretty wide margin. The same is true for Y2 on the right, on the upper right. The black trace is significantly higher than the green trace. But now on the lower two traces, I've got the same results for test B. And here, the green trace is much closer to the black trace, indicating that the response for Y1 and Y2 is more linear for test B. The other measure is the partial coherence. Here I'm showing on the top the partial coherence for Y1 and Y2 for test A. Now, as you can see, and B, as you can see, the green trace for test B is the partial coherence between Y1 and Y2. Y1 and drive 1 is higher than for test A, where the black trace, where it's also the same measure. So this shows that the relationship between drive 1 and Y1 is more linear. On the right, I've got the similar result for Y2. Again, I have the green trace is much higher than what you see for the black trace, again indicating that that Y2 is operating more linear. On the lower row, I've got the same sort of results for Z1 and Z2, the vertical actuators. And now again, you can see that the green trace is much higher than the black trace, particularly on the lower left, where at the high frequencies it's much higher, almost 0 for test A and almost 1 for test B. Same sort of result on the right. Well, this then shows that the new MIMO random test results that the optimal adaptive control and new optimized reference reduce the control error in the least mean squared sense. It uses reduced power needed to drive multiple shakers. The new synthesis matches the initial reference in the least mean squared error sense. It compensates for test system and facility limitations, as I've shown you by showing you the modified references. It's a better match of the controls to the pre-specified PSDs. It's a better matching of control coherence to the new reference. Better uniformity of controls with a rectangular control. It improves the linearity of the shaker systems and better match between control responses and respective MCOPs. And improves the partial coherence between control accelerometers and respective shakers. Advanced adaptive optimal MIMO control produces a closer matching to references than other approaches by optimizing each control loop. The new synthesized positive definite control reference, SDM, further improves control and avoids trial and error approaches used by other methods. An optimized reference improves uniformity via rectangular control by using the new synthesized control reference, which approximates a predetermined initial control SDM in the LMSSC sense. The new minimum drive power control reference SDM is synthesized by the underlying optimization methods and new research during an initial pretest. The use of the new control reference SDM further reduces the needed power to improve control accuracy and linearity by accounting for limitations in the test system and facility as an optimization constraint. Well, thank you very much. That's my talk. I'm open to your questions now. Thank you very much.